welcome to another module in this massive open online course. So, we are looking at the Fourier analysis for discrete time signals. In particular, we are looking at the discrete Fourier series. So, let us continue our discussion on the discrete Fourier series. So, we are looking at the Fourier analysis of discrete time signals. In particular, we are looking at what is known as the discrete Fourier series. In particular, we are looking at the discrete Fourier series, okay, where a signal x of n can be expressed as periodic signal, periodic discrete time signal can be expressed as xn can be expressed as summation k equal to 0 period n naught, that is periodic discrete time signal with period n naught can be expressed as summation k equal to 0 to n naught minus 1 c k e raised to j k omega naught n, okay. And similarly, the inverse discrete Fourier series, that is the coefficient c k, can be derived as 1 over n naught summation n equal to 0 to n naught minus 1 x n e raised to minus j k omega naught n. So, this is your discrete Fourier series, this is your inverse discrete Fourier series, that is to derive the coefficients c k. Let us now look at another interesting aspect of this discrete Fourier series, which is basically the duality property of the discrete Fourier series. So, duality, so remember we have xk, as we already said, the discrete Fourier series is xn equals summation k equals n naught minus 1 c k e raised to j k omega n. What can we say about the sequence with c k equals c n? That is, what can we say about this sequence? That is, when, remember, duality is about when you have, for instance, when the Fourier transform, when a signal small x of t has a Fourier transform capital X of h, x of f, what happens, or capital X of omega, what is the Fourier transform of the signal capital X of t? That is what, that is the frequency domain becomes the time domain, what is the corresponding Fourier transform of the signal. Similarly, if the sequence c k becomes a time domain signal, now remember we already said c k is periodic, remember that is what we have derived in the previous module, c k is periodic with period equals n naught, implies that the time domain signal c n is also periodic in time with again period equals n naught. Now, further, if you look at this, you have x n equals summation c k e raised to j k omega naught n. If you consider x of n naught minus n, then that is summation k equal to 0 to n naught minus 1 c k e raised to j k omega naught n naught minus n, which is equal to summation k equal to 0 to n naught minus 1 c k e raised to j k omega naught n naught. Now, omega naught, recall, is 2 pi over n naught, which implies omega naught n naught is equal to omega naught n naught equals 2 pi. So, this reduces to C k e raised to j k omega naught n naught or e raised to j k 2 pi into e raised to minus j k omega naught n. And we know e raised to j k omega 2 pi, e raised to j k 2 pi is 1 for any integer k. So, therefore, this quantity here is 1, and what we are left with is we are left with this quantity k equal to 0 to n naught minus 1 C k e raised to minus j k omega naught n. So, now x of n naught minus n, correct, x of n naught minus n is C k e raised to minus j k omega naught n. Now, we make C k equal to C n and we make x n equals x k, that is the previous x n equals x k. Then what we have from this statement is basically that x of n naught minus k equals, remember k becomes n, k equal to 0, summation n equal to 0 to n naught minus 1 C n e raised to minus j k omega n. Now, if you look at this summation C n e raised to minus j k omega naught n, this is similar to this summation n equal to 0 to n naught minus 1 x n e raised to minus j k omega naught n, except for this factor 1 over n naught. So, what I am going to do is I am going to multiply and divide by this factor n naught. So, now you have 1 over n naught times n naught, and now you can see if I call this as the C tilde of n, now you can see that x of that is C tilde of n, that is this is basically identical to the inverse discrete Fourier series. This is the identical to the inverse discrete Fourier series, where you are basically coefficient x n naught minus k, that is C tilde of n has basically the discrete Fourier series coefficient x n naught minus k, which is equal to x of minus k, because remember x is a periodic sequence, x of minus k. Okay. So, basically if you look at that, you can say C tilde n, or basically if C tilde n equals, remember this is 1 over n naught C of n. So, 1 over n naught C of n has basically the discrete Fourier series x of minus k, or going back to the original notation C of n or C of k, take the n naught to the other side, is basically has the discrete Fourier series representation, that is n naught x of minus k. This is the duality property. Or x of this is basically x of, or C of n is basically has the discrete Fourier series coefficients x of minus n naught times x of minus n, that is if C k is become a time domain signal, then the corresponding discrete Fourier series coefficient, the coefficients of the discrete Fourier series are given by n naught times x of minus n. So, this basically is the duality property. Or you can also write it, since we are denoting time domain by the brackets, you can also write C of k in the time domain becomes n naught x of minus n. Depending on which notation you are comfortable with, you can appropriately write this thing. Okay, both this thing means one and the same. C of n equals C of k, x of minus n equals x subscript minus n equals x of minus n. Okay. So that is basically the duality property for the discrete Fourier series. Now what happens when we consider a real signal? Let us consider the property of a DFS, the discrete Fourier series of a for a real signal xn, when xn is a real signal, when xn is real, which implies x conjugate of n equals xn, because xn is a real signal. Then we have, remember from the discrete Fourier series or from the inverse discrete Fourier series, remember Ck is 1 over n naught summation n equal to 0 to n naught minus 1 xn e raised to minus j k omega naught n. Now C of n naught minus k, this is equal to 1 over n naught n equal to 0 to n naught minus 1 xn e raised to minus j k omega naught, or e raised to this k is by n naught by minus k. So, e raised to minus j n naught minus k omega naught n, which is, once again you can substitute this as 1 over n naught summation n equal to 0 to n minus 1 xn e raised to minus j n naught omega naught is again 2 pi e raised to minus j 2 pi n into e raised to minus j omega naught n. Now this quantity is 1 e raised to minus j 2 pi n. So this reduces to 1 over n naught summation n equal to 0 to n naught minus 1 xn e raised to minus j omega naught n. This is C of n naught minus k, which means C of n naught minus k conjugate equals 1 over n naught summation n equal to 0 to n naught minus 1 x conjugate n e raised to minus j omega naught n conjugate, that is e raised to j omega naught n. But x conjugate of n equals xn. So, for a real signal this is simply 1 over n naught summation n equal to 0 to n naught minus 1 xn e raised to j omega naught n. And if you look at this, this is simply your C of k. So, C conjugate n naught minus k C conjugate n naught minus k equals C of k. So, this is the property for a real signal. There is C conjugate of, and remember C of n, C is a periodic sequence. So, C conjugate C of n naught minus k is basically C of minus k. So, you can also write this as C conjugate of minus k equals C of k. Again this is for a periodic signal. Okay. So, basically what that means is that is C cos. So, it has the magnitude has an even symmetry. So, C conjugate of minus k is basically C of k, okay, all right, and C conjugate of basically n naught minus k, correct. C conjugate of n naught C conjugate of n naught minus k is basically the same thing as C conjugate of minus k, because it is periodic with n naught, okay, all right. And finally, let us also look at one final property, that is the Parsevals relation, which is of course an important Parsevals theorem for the discrete Fourier series. This is the Parsevals theorem. Energy of the DFS coefficient summation k equal to 0 to n naught minus 1 magnitude C k square. Now, this is, if I look at the corresponding time domain, that is summation k equal to 0 to n minus 1 n naught minus 1. Now, I am going to replace the expression of the C case by the inverse discrete Fourier series 1 over n naught summation n equal to 0 to n naught minus 1 x n e raised to minus j omega naught e raised to minus j k omega naught n whole square, okay, which is equal to summation k equal to 0 to n naught minus 1 over n naught square. I am going to write this as the magnitude square is the quantity times its complex conjugate, correct. Magnitude a square is a times a conjugate. So, I am going to write it as the summation into its complex conjugate. So, this is summation n equal to 0 to n naught minus 1 x n e raised to minus j k omega naught n, its complex conjugate. I am just going to change the index and I am going to rewrite this as summation m equal to 0 to n naught minus 1 x m e raised to minus j k omega naught m complex conjugate, okay. Now, if I expand this, I can bring the 1 over n naught square outside since it is constant. Summation k equal to 0 to n naught minus 1 summation n equal to 0. So, there are going to be 3 summations, n equal to 0 to n naught minus 1, m equal to 0 to n naught minus 1 times x n into x m conjugate. So, times x n into x m conjugate into e raised to minus j k, all right, e raised to minus j k n minus m omega naught, which is equal to, now I interchange the summation. So, I will bring the summation with respect to k inside. So, that will give me summation n equal to 0 to n naught minus 1 summation m equal to 0 to n naught minus 1 summation k equal to. So, now this will be, since x n and x m do not depend on k. So, I will bring the x n and x m as well outside, and the last summation is summation with respect to k equal to 0 to n naught minus 1 e raised to minus j k n minus. Now, this summation you can clearly see summation k equal to 0 to n minus 1 e raised to minus j k n minus m omega naught. This is equal to, remember, e raised to minus j k n minus m omega naught over one fundamental period, that is omega naught. The summation of any complex exponential which has fundamental period omega naught, fundamental period n naught over n naught is basically 0 if n is not equal to 0 is n is not equal to m, and if n is equal to m, then simply it is simply summation 1 which is n naught. So, this is equal to 0, n naught equal to m equal to n naught if n equal to m. So, effectively this is basically equal to n naught delta n minus m, that is if n equal to m, this is delta 0 which is 1. So, this is n naught into 1, otherwise if n is not equal to m, then this is delta n minus m which is 0. So, this is basically simply 1 over n naught summation n equal to 0 to n minus 1, or this is 1 over n naught square, in fact 1 over n naught square summation m equal to 0 to n naught minus 1 xn into xm conjugate into n naught delta n minus m. So, the n naught over n naught square gives n naught summation n m, the delta n minus m means only terms which n equal to m survive. If n equals m, then xn into xm conjugate is magnitude xm square. So, this is summation n equal to 0 to n naught magnitude xn square. So, that is the Parsevals relation. So, Parsevals relation tells us that basically Parsevals relation tells us that for the discrete Fourier series summation k equal to 0 to n naught minus 1 magnitude ck square equals 1 over n naught summation k equal to 0 or summation n equal to 0 to n naught minus 1 magnitude xn square, and this is your Parsevals relation. This is the Parsevals relation for the discrete Fourier series. All right. So, this basically completes our discussion of the discrete Fourier series. All right. So, basically we have looked at the discrete Fourier series representation of a periodic discrete time signal with fundamental period n naught. We have looked at its several properties, and also for instance such as the duality property, the Parsevals relation, etc. So, we will stop here and start with another transform, which is the discrete time Fourier transform for discrete time aperiodic signals in the subsequent module. Thank you very much.